Section 10-3 is on the average value of a function. The objective of this section is to calculate the average value of a function. All right, so let's start out with average velocity. And average velocity, if you go back and think about how you calculate your average velocity, or your average speed, if you will. If you're traveling from point A to point B and you know how far you've traveled, that is, if you know your displacement, then to find out your average velocity, you just take that displacement, divide by how much total time that took you to make that trip, and that tells you your average velocity. So in other words, to calculate average velocity, we'll call that V sub AV, is equal to your displacement divided by your time, your total displacement divided by total time. But of course, we know that your displacement from the last section is equal to the definite integral from A to B of your velocity function. And your time then is the interval from A to B, that's B minus A. So in other words, if we take and divide those two, that gives us our average velocity. Or sometimes we even rewrite that and pull the B minus A out front, so it's 1 over B minus A times the integral from A to B of V of t dt. So if you want to find the average velocity, in other words, you integrate velocity, the same function, and then divide by the interval. Integral divided by interval. Well, let's try that with average speed. If you want to calculate average speed, again, to determine what your average speed is for some trip from point A to point B, you need to know how far you traveled, your distance, and then how much total time it took to make that trip. And you divide those two. Distance divided by time will give you your speed. And we know from the last section that your distance is equal to the definite integral from A to B of the absolute value of velocity. And your time then is the interval from A to B. That's B minus A. And again, sometimes we rewrite that and pull the B minus A out front and write it as 1 over B minus A times the integral, a definite integral from A to B of the absolute value of velocity with respect to time. So again, to find your average speed, you integrate your speed function, which speed is the absolute value of velocity, and you divide by the interval from A to B. So it's integral divided by interval. So again, to find the average velocity, you integrate velocity. To find average speed, you integrate speed, that same function. All right, let's extend this to just any function. That if I have a function f of x and I want to find the average value of f of x, that is, I want to take all the y values in essence in that function and average them out. That's what the average value actually is, taking all the y values that that function has and averaging it out. The way to do that is the same calculation here. If I want to find the average of my y values, that's y sub AV, we'll call that. It's equal to the definite integral of your function f of x dx from A to B divided by the interval from A to B. That's B minus A. Or again, you can see that we sometimes pull the B minus A out front and write it as 1 over B minus A times the integral from A to B of f of x dx. So again, it's the interval, or excuse me, the integral divided by the interval. So to find the average value of a function, you integrate that function to do it and divide it by the interval. Now, to help see why that is, let's take a quick look at a proof here that kind of illustrates this for us. We're not going to look at the formal proof of it, but we'll look at the basic idea of the proof. If I just take some function here, we'll just sketch some function here on some interval. We'll say that this is f of x. And we'll pick some interval, let's say from right here will be a to, we'll call this b right here. And if we want to find out the average value of this function, again, what that means is I want to take all of these y values. If I could take every single one of these y values, which is all these guys right here, add all of them up. Now, there's an infinite number of them, so I can't add them all up. But if I could add them all up and divide by how many there are, that's my average y value. But it turns out there's some value then that's about maybe right going to have to approximate it, maybe about right here. That's the average. This is y sub AV, our average y value. Some of the y values are above that, some are below it, and we add them all up, divide by how many we have, and that tells us the average. Well, it turns out that if I were to look at this region here from A to B, and I were to take this area that's above the average value, and if I could kind of slide some of this area over here and slide some of it over here, I didn't quite draw my average y value quite high enough there. It should be a little bit higher, but what I end up with is a rectangle whose area is exactly the same as the area of my definite integral from A to B. And so those two, since I'm just moving area from under the curve to fill in these little gaps here to end up with this rectangle, those two areas must be the same. The area of the rectangle is equal to your definite integral. Which, of course, the area of the rectangle, I know area of a rectangle is an area of base times height. So the base of this thing is this distance right here, this horizontal distance from A to B. That's our base. And this distance up to our average y value, that's the height of our rectangle. So I can find the area of it, base times height. The base is going to be b minus a. And the height of it is actually what y sub AV is measuring, my average y value. And we said that's equal to the definite integral. The definite integral, of course, is the integral from a to b of f of x dx. And if I want to solve for the average y value, just divide by the b minus a. So I end up with y sub AV is equal to 1 over b minus a times the integral from a to b of f of x dx. There is our average value of a function. All right. And with that, there's one last thing that we should talk about, which is the mean value theorem for definite integrals. And there's one condition for this theorem. If you recall, we've talked about a mean value theorem for derivatives. And now this just extends it to definite integrals. It says if one, there's only one condition here. If f is continuous on a closed interval from a to b, then there is at least one point, x equals c, in the closed interval from a to b, for which f of c is equal to this average y value. So there's got to be at least one point where we are equal to this average y value. And if I go back to the previous sketch that we had here, the little proof that we did, I've kind of got quite a few things marked on this thing, but this point right here would be one such value of c. And this point right here would be another such value of c. Those would be potential values of c, where the function itself and the average y value are the same. And the c value, of course, is the x value where that happens. Okay, so that's the Funwell theorem the mean value theorem for definite integrals. All right, let's take a look at an example, and I'm going to modify their example that they gave us here. But if you look at example 1, it says for the function v of t is equal to 12t minus t squared. It says, which is graphed there on the previous page, find a value of t equals c for which v of c equals the average velocity, which is 29 feet per second. Now, they kind of gave you more information than I was hoping they would for this problem, but that's the way they set it up, so we'll deal with that. Instead, I'm going to change it and find the average velocity of the function in the interval from 2 to 11, which they already told us the answer is 29. We're just going to verify that, in fact, we get that. So the average velocity, v sub AV, we said is equal to the integral from 2 to 11 of my velocity function, which is 12t minus t squared dt, divided by the interval, which is 11 minus 2, or I prefer to write it as 1 over 11 minus 2. Just put the constant out front, and then go from 2 to 11 of my velocity function, which is 12t minus t squared dt. Okay, you can write it either way, but that's how we calculate this. We're just going to run this through our calculator here. You could use Fundamental theorem certainly to evaluate that, but let's use our calculator since we have it. And we'll tell it to do the numerical integral of 12. I'm going to do this in terms of x minus x squared. My variable is x, and I'm going to integrate from 2 to 11. And I'm just going to divide that by the quantity there, 11 minus 2, or divide that by 9. That's what I'm looking for, is what the final result is. And hey, look at that. We get 29. All right, and as far as units are concerned, if you look at your calculation here, we're actually calculating this quantity right here, which is the integral of velocity. Integral of velocity is going to give us our displacement, so that's measured in feet. And we're dividing that by this quantity right here, which that quantity right there is our time. So that's divided by our time, which is measured in seconds. So if you look at your calculation helps you find the correct units for the problem as well. So it's 29 feet per second, just like they told us there. All right, let's take a look at the second part of this now, or what I'm going to make the second part of this, I guess. And for part B, it says to find the point C in the interval from 2 to 11 at which the conclusion of the mean value theorem for derivative or for definite integrals is true. Basically, that's the question they asked you to do. And to find that value of C, all I got to do is take the average velocity that we came up with and set it equal to my velocity of curve. Okay, basically I'm taking f of C and setting it equal to my average velocity. Whoops, we called that v sub. Let me try that again. My function is not f, my function is v. My velocity function at C has to be equal to my average velocity, v sub av, is basically the equation that we're setting up. That's what we had on that slide that had mean value theorem laid out for us. So v of c is just taking your velocity function and plugging in c. You can either put it in terms of c or leave it in terms of t. It doesn't really matter to me. But if we put it in terms of c, it would be 12c minus c squared. And we want to find out where that's equal to our average velocity that we just calculated up above here was 29. So you have a quadratic equation here that you want to solve to find out the value of c. I'm just going to rewrite this as c squared. I'll move this stuff to the right. C squared, c squared minus the 12c plus 29 equals 0. I want to find out my solution there for c. And of course, I want the solution that's in the interval from 2 to 11. So I'm just going to run this through my quadratic formula program on my calculator. You could graph this as well. It'd be another way you could find that solution, but I'm just going to run my quadratic formula. So A was 1, B was a negative 12, and C is 29. And so we get 8.646 is our first solution. 8.646. And the second solution was at 3.354. 3.354. All right, so it turns out there's actually two solutions there that we end up with. These are both in seconds, of course, where the average value of our function is equal to 29. All right, and you could graph this and actually see that intersection there like we saw on the example that we sketched, but let me just do that on the calculator here real quick. If we graph 12x minus the x squared, I'm going to graph 29 along with it, and we'll set our window to go from 2 to 11. And we'll go from 0 to, I know the solution I'm looking for is at 29, so I'm just going to go from 0 to 50. I guess we'll leave that and graph it. And you can see there's the two solutions. If you graph, find those intersections, that's exactly what we found here.